Hello everyone. In this video lecture, we will be discussing about the root locus technique. So, what is the root locus? A root locus is the the locus of roots of the characteristic equation for different values of k, which will be ranging from 0 to infinite. So, it is a locus of roots for different values of k. K means here gain. Okay, now there are some certain steps which is to be followed in order to draw the root locus accurately. So one by one we will see those steps. For your reference, I have already written down the steps on the left hand side of the slide, so you can follow these steps from there as well. So step number one, in step number one, it says that locate the open loop poles and zeros in S plane. So, given the open loop transfer function, the first step is to locate the open loop poles and zeros on S plane. So, what you have to do, you have to draw the S plane, and on this S plane, you have to draw the poles by cross sign and zeros by a circle sign. So, this is the first step of drawing the root locus. Second step, any point on the real axis is a part of root locus if total number of open loop poles and zeros to the right of that point is odd. You can see any point on the real axis is a part of root locus if total number of open loop poles and zeros to the right side of that point is odd. So what does this point says? Suppose after locating points and zeros from step number 1, we are having the location of poles and zeros like this. Let us suppose we are having this as a poles and zeros. Just randomly I have drawn. So what does this step says? Any point on the real axis is a part of root locus if the total number of open loop poles and zeros to the right hand side of that point is odd, right? So let us consider this pole and look to the right hand side of this pole. Now when you observe to the right hand side, you can see that there are no poles on the real axis, no poles or zeros on the real axis. So that means 0, right? So which is not odd. So from this point onwards to this point, that means on the real axis, it will not be a part of your root locus, right? Now let us consider that you are at this point. Second step, just a second. Now let us consider that you are at this point and look to the right hand side of this point. Now when you are looking at the right hand side of this point, you can observe that there are one pole on the real axis, right? What you have to see, are there any poles and zeros on the real axis? And which is our real axis? This is our real axis, right? Which is where the imaginary part is 0. When you are looking to the right hand side, you can observe that there is one pole on the real axis, so which is odd. So according to our definition of step 2, so this from this point onward to this point will be our part of our root locus, right? Now let us consider that you are at this point and again look to the right hand side of this point, and while observing from this point, you can see that there are two poles which are lying on the real axis. Again we have to consider the real axis because right now we are discussing about whether the real axis will be a part of your root locus or not, or which part of the real axis will be the part of your root locus. So when you are standing here or when you are observing from this point, look towards the right hand side, and while you observe that there are two poles on the real axis, that means this will not be a part of your root locus, right? Again move to this point and observe to the right hand side. Now when you are observing, you can see that there are 1 0 and there are two poles, so that means total number of poles and zeros will become 3. Again keep in mind that poles and zeros should be on the real axis, right, which is there in our case. So you can see that total number of poles and zeros on the real axis to the right hand side of this pole is 3, so that means this will be part of our root locus, right? Now when you're for the last instant when you are at minus infinite and when you are observing from minus infinite, see at any point after this pole on the left hand side, at every point from here onwards to minus infinite, the total number of poles and zeros on the real axis will always remain 4, which is even. So this will not be a part of our root locus, right? So to be very precise, let me draw what will be the part of root locus and what not. So what we have discussed from this step number 2, that this will be our part of root locus and this real axis will be part of our root locus. So this is step number 2 that we have seen, right? Now moving to next step, that is root locus is symmetrical about real axis. It originates from open loop poles at k is equal to 0 and it terminates at open loop 0 at k is equal to infinite. So let us just give us a glance on this step number 3. Okay, so just see, root locus is symmetrical about real axis. What does it mean? Let us suppose we are having the real axis like this, that is sigma and j omega, and this is our S plane. So real axis, which is our real axis? You can see this is our real axis. So symmetrical about real axis means, it means that if suppose this is the root locus for some values of gain k, then it will have the mirror image of it on the left hand, on the minus side as well. So you can see that this is symmetrical to this, right? So you do not need to draw these two parts separately. What you can do, you can draw the top half and then you can draw the mirror image, and that will be exactly same as the top half. Or you can say that it will be having the mirror image. So that is what we call it as a symmetrical image. Symmetrical about real axis, right? So we can observe that root locus is symmetrical about real axis, right? And it is also saying that it originates from open loop poles at k is equal to 0 and it terminates at open loop 0. So that means at open loop poles, the value of k is 0, and at open loop 0, the value of k is infinite. So for example, let me just draw very roughly the poles and zeros of any arbitrary system. This is real axis, this is j omega. Let us suppose I am having one pole here and one zero here, right? I have drawn like this. So that means this will be our part of our root locus, because when you're standing here, you can see that from step number 3, total number of poles and zeros on the real axis will be 0. So that this will not be part of your root locus. When you're standing here, when you're observing to the right hand side, you can see that total number of poles and zeros on the real axis is 1, which is odd. So this will be part of your root locus. And from this point onward to minus infinite, this will not be part of your root locus, right? So only this part of real axis will be part of your root locus. And from step number 3, we have seen that at open loop pole, the value of k is 0, and at open loop 0, the value of k is infinite. And what is so it originates from open loop poles. That means it originates from open loop poles. That means arrow will go from poles to 0. So this is regarding the step number 3. Now let us see the step number 4. What does step number 4 is saying? The point at which the root locus branches leave or approach the real axis is called breakaway point or break-in point. It can be determined by dk by ds equal to 0. Right? So the point at which the root locus branches leave or approach the real axis. So I am giving you one scenario where you can see what is the breakaway point and what is the break-in point. First, you have to understand what is the difference, right? Right. So let us suppose that I have drawn the S plane and I am having two poles here and here. Now, when you are observing to the right hand side of this pole, you can see the total number of poles and zeros will be odd. So that means this hole will be my part of my root locus. Let me change the color. So this hole will be part of my root locus, right? And from step number 3, we have seen that At open loop pole, the value of k is 0, and at open loop pole, the value of k is 0. That means both are open poles, and the root locus branches will start from open loop pole. So you can see that these two branches will come together at one point. Let us suppose say this is that point by circle, or let us say this is the point, right? Now when they intersect at that point, uh, then it is a rule that a single point cannot be a part of two root locus lines, right? So a single point cannot be a part of two root locus lines. That means after intersecting, they have to dissect, or they have to divert each other. Both of the root locus branches, which is coming from both of these poles, will divert from each other points, right? So let me show you that. Okay. So this start from here and this start from here, and randomly I'm drawing that this root locus branch will leave like this, and this root locus branches will leave like this, right? So this point will be called as break away point. And what is break in point? For that, again, I have to draw one scenario, that is sigma, that is real axis and imaginary axis. And let me take again another pen, another color. So let us suppose there are two zeros, right? And you know that value of gain at 0 is infinite. So I can write here infinite, k is equal to infinite, and root locus branches terminate at infinite. That means it will be coming like this. So this root locus branches has to come from somewhere, right? So that means it can just randomly I'm drawing by freehand. So one branch can reach from here, another branch can reach from here, right? So you can say that this is our break in point, right? So this is the difference between breakaway and break in point. In breakaway point, you can see that we are having two poles. In break in point, we are having two zeros, right? And how to calculate breakaway and break in point? You can do dk by ds is equal to 0, right? How you can find out k? You can find out the value of k, or equation of k, from characteristic equation. And what you can do, you can put the k on the left hand side and all the other elements or all the other terms of the characteristic equation on the right hand side, and then you can differentiate it with respect to s and equate it to 0, and you can calculate that value of s which satisfy the value of this breakaway point or break in point, right? So this is step number 4. So I hope this step number 4 is also clear. Let us move to next step. Step number 5. So angle at which the root locus branches leave or approach the breakaway or break-in point is given by plus minus 180 by r, right? So angle at which root locus branches leave or approach the breakaway or break-in point. Again, let us consider the same scenario. Now I'm not writing real and imaginary, right? Imaginary point, right? You can assume that this is the S plane, where x-axis representing the real part and y-axis is representing the imaginary part, right? Now let us consider the same condition. We are having two poles. Now each root locus branch will start from each of the poles, and then they will intersect at some point, which is called as breakaway point. Away point, right? And then they can leave. Now how they will leave after breakaway point? Because there are infinite number of ways the branch can leave, like this, leave like this, leave like this. Any of the way the root locus branches can leave, right? Or it can, one branch will go in the downward direction or any direction, right? So what will decide, or at which angle this branch will leave the real axis? So that angle you can calculate it by 1 plus minus 180 by mod r. So where mod r is what? Where mod r is what? Mod r is the number of root locus branches leaving or approaching the breakaway or break-in point. That means how many branches is approaching that breakaway point is given by r. In our case, in our example that we have considered here, so how many branches is approaching this breakaway point? You can see there are two branches. One branch is from this pole, another branch is from this pole. That means r will be equal to 2. So that means plus minus 180 by mod r. That will give you plus minus 180 by 2. That means plus minus 90 degree, right? So after breakaway point, one branch will leave like this and another branch will leave like this at an angle of plus 90 and minus 90. I hope this is clear. That is step number 2. Similar case will be for the break in point. In break in point, just the opposite of breakaway point, we are having two zeros here. And how this breakaway point, how the root locus branches will approach to this real axis will be given by plus minus 180 by r, where r will be again number of branches approaching that break in point. So how many branches is approaching this break in point? At this point there are two branches, so again it will be plus minus 90 degree, right? It might happen that there are four branches which is approaching or leaving the breakaway or break in point. In that case, mod r will be equal to 4, right? So this is regarding the step number 5. This will be more clearer when we will solve some of the examples. So let us just go through all the steps of performing the root locus, then we can solve the examples. Okay, now let us look at this into the step number 6. So if the number of open loop poles are greater than number of zeros, right? That is, poles are greater than zeros, then number of root locus branches terminating at infinity will be given by p minus z. P minus z branches will terminate at infinity, right? Where p is equal to number of open loop poles, as you can see, z is equal to number of open loop zeros, right? So this step is quite easy. As you can see, you can calculate the number of poles and zeros directly by the open loop transfer function. If number of poles is equal to number of zeros, then no branches will terminate at infinity. But if poles is greater than number of zeros, then some branches will terminate at infinity. And there will be no condition when number of zeros will be greater than number of poles, because this condition is not physically realizable. Not physical realizable, right? Or that means you cannot have an hardware where the number of zeros are greater than number of poles. So you can have two things only: either the poles are greater than 0, or poles are equal to 0. If poles are equal to 0, no branches will terminate at infinity. If poles are greater than 0, then p minus z branches will terminate at infinity, right? So this is regarding the step number 6. Let us see step number 7. So number of root locus branches is equal to number of open loop poles or number of closed loop poles. You can see number of root locus branches is equal to total number of open loop poles or number of closed loop poles. Therefore, number of root locus branches is equal to order of the closed loop system, right? So you can see here how many branches a root locus will have will be decided by the number of poles, obviously, because the number of poles will be always be greater than or equal to number of zeros, right? You can calculate how many poles are there either by the open loop transfer function, closed loop transfer function, or you can also calculate the order of the transfer function. I hope you know what is type and order of the system. So if you want to learn it again, so let me draw it again, show you again. So there are two terms which is called as type and order, and both are related with your open loop transfer function. Type says number of poles at origin. If there are two poles at origin for open loop transfer function, then we can say that it is having the type 2 system, it is type 2 system, and order is total number of poles. Right? So this is step number 7. What does step number 7 says? The total number of root locus branches is equal to the number of open loop poles or number of closed loop poles, or equal to the order of the control system or order of the closed loop system. So let us see step number 8. That is step number 8. The root locus branches terminating at infinity will do so along a straight line called asymptotes, right? Consider that case where p is greater than 0, that is poles are is greater than 0. In that case, p minus z branches will terminate in infinite, right? And how that branches will terminate at infinite? Because it should have some direction, right? And that direction will be given by asymptotes, right? So in the next step, we will be seeing how to calculate the asymptotes, how to draw the asymptotes, right? So what is asymptotes used for? It is used to you can say how our branches which are terminating at infinite are doing so along that line. So let us see next step. That is step number 9. So angle of asymptote is given by, so this is the angle, alpha is equal to 180 degree 2q plus 1 upon p minus z, where q is equal to 0, 1, 2, 2, p minus z minus 1. So this is the formula of calculating the alpha, that is angle of asymptote, right? So you can see when p minus z is equal to 1, this condition, when p minus z is equal to 1, that means one branch will terminate at infinite, and for it the angle will be 180 degree. When p minus z is equal to 2, then we will be having values of q will be 2, and we are having two different alphas. When p minus z is equal to 3, we are having 3 values. You can see when p minus z is equal to 4, we are having 4 values, right? We will be seeing this while we will be solving some of the examples, then it will be more clearer, right? So why asymptote is used? Because if poles are greater than zeros, then some branches will terminate at infinite, and at what angle that branch will terminate at infinite will be given by the angle of asymptote. Now next point, there is step number 10. So the point at which the asymptote intersect the real axis is called centroid or center of gravity, which is given by sigma. So centroid, this is the next term, it's given by sigma. And what is centroid? The point at which asymptote intersect the real axis, because asymptote is given by the angle, you can see, which we have calculated from here to here. Now this angle has to be drawn from some point, right? And that point will be given by the centroid, and that centroid will be on the real axis, right? So the point at which the asymptote intersect the real axis is called centroid or gravity. How you can calculate centroid? That is summation of real part of poles minus summation of real part of zeros divided by p minus z, right? So how you can calculate poles and zeros? You can calculate poles and zeros from your open loop transfer function, and you have to calculate the real part of poles minus real parts of zeros upon p minus z. From this point, you can calculate the centroid, and from that centroid, you can draw the asymptotes, right? We will be seeing this centroid when we will be solving some of the examples. So that in that time, it will be much clearer. Next step, that is step number 11. The point of intersection of root locus branches on the imaginary axis can be determined by applying the condition of marginally stable system in Routh's table, right? So what does this point is saying? Suppose if you are having the root locus like this, right? So you can see that this root locus branches is intersecting at imaginary axis. You can see at this point and at this point it is intersecting with the imaginary axis. Now you can determine these points by using the Routh table, right? But how you can determine by using Routh table? You can apply the concept of rows of zero, that is ROZ, that is rows of zeros, and then you can calculate this point. Again, this point will be more clearer when we will be solving some of the examples, right? So this is regarding the step number 11. Let us just move for now to the next step. That is step number 12. So angle of departure, it is the angle at which root locus branches depart from open loop poles, phi d. Okay, so this is called as angle. Next term is angle of departure, which is given by phi d. And why we need this angle of departure? Because suppose if we are having the complex conjugate poles like this, right? And you know that at poles the value of gain is equal to 0, right? And poles the value of gain is equal to 0. Now that and from poles the root locus branches originate, right? So a root locus branch can originate from this pole in infinite direction, right? It can go like this, go like this, go like this. Many directions can be there, right? I'm not drawing the for this pole because it will be just the mirror image of the top one, right? As we have already discussed in step number 3, that is root locus is symmetrical about the real axis, right? Now at which direction the root locus branches will go from this pole will be given by angle of departure, right? So that is why we calculate the angle of departure, and angle of departure is given by phi d is equal to 180 degree minus phi p minus phi z. right? And here there are two terms, that is phi p and phi z. And what are those phi p and phi z? You can see from this point, phi p is what? Angle contributed by open loop poles, by other open loop poles. And phi z is what? Angle contributed by open loop zeros, right? So suppose if you're calculating the angle of departure for this pole, right? And so phi p for this will be angle, phi p will be angle contributed by all the other poles. So in this case, there is only one pole. So you have to calculate what is the angle contributed by this with uh, uh, with moving from left to right, right? You can calculate the angle of departure. You can calculate the phi p angle from here, right? You can measure the angle from the right hand side towards the left hand side in a anti-clockwise direction. So angle will always be measured from in an anti-clockwise direction, right? So this will be, again, we will be seeing when we will be solving some of the numericals. And phi z is again the angle contributed by the zero. In this case, we are not having any zero. So let us consider that this is 1 0. I am putting 1 0 here. So you can calculate the angle contributed by here as well. So phi p and phi z will be this point. So this is phi p and phi z. You can substitute the value of phi p and phi z here, and then you can calculate phi d, right? Similarly, with respect to the angle of departure, we are having the angle of arrival as well. And angle of arrival, now you can guess that angle of arrival will be calculated for complex conjugate zeros, right? If you're having an S plane, and suppose if you are having complex conjugate zeros at open loop, at this zeros, value of k will be equal to infinite. We have already seen, and at zeros the root locus branches will terminate, right? So that means root locus branch can come in from any direction, it can come, right? So in which direction it will come, from which direction it will come, will be given by the angle of arrival. And angle of arrival is given here, that is phi a is equal to 180 degree minus phi z minus phi p. The only difference from angle of departure is here we are having phi z first, then we are having phi p. You can compare it with this formula, right? It is comparable. It is quite comparable. So there are two terminologies, that is phi d and phi p, right? So I hope this step number 13 is also clear. Now we will see next step, that is step number 14. Now we will see the magnitude criteria, right? And how you can calculate that. This is the characteristic equation which is given by 1 plus gs hs is equal to 0. 1 plus gs hs is equal to 0, and gs hs will be equal to -1. So you can take the mod, that is mod of gh will be equal to 1, right? So this is what we call as a magnitude criteria, right? So why this magnitude criteria is used for? The magnitude criteria of open loop transfer function, at any point on the real axis is 1. It is used to determine the value of k at any point on the real axis. It is used to determine the value of k at any point on the real axis. So in this gh, we are having it in terms of k and s, right? And so you can put the values of s. That means for any point, you can calculate the values of k and k, right? So this is the magnitude criteria. Similarly to the magnitude criteria, we are having the angle criteria as well. This is given by again 1 plus gs hs is equal to 0. So gs hs will be equal to -1. That means angle of gh will be equal to odd multiples of 180 degree. That will be equal to 2k plus 1 into 180 degree. That means, and value of k will be ranging from 0, 1 to infinite, right? That means at any point on the root locus, the angle of root locus is odd multiple of pi or 180 degree. It is used to determine the shape of the root locus, right? So there are two conditions, angle criteria and magnitude criteria. Magnitude criteria, we have seen, it is used to determine the value of gain k, and this is the angle criteria which is used to determine the shape of the root locus, right? Now since we have seen all the steps, what I will do, I will just recollect the various steps that we have gone through before jumping into the solved examples. So let me just clear the slides. Okay, so what we have seen so far is that we are studying the root locus technique. It is drawn for the gain k is equal to 0 to infinite, as you can see. Now there are certain steps to draw the root locus. First step is to locate the open loop poles and zeros on S plane. This we have seen. Any point on the real axis is a part of root locus if total number of poles and zeros to that part is to the right hand side is odd, right? This is also a step we have seen. Third step is root locus is symmetrical about the real axis. It originates from open loop pole. That is, at open loop pole, the value of gain is equal to k is equal to 0, and at open loop 0, the value of gain k is equal to infinite. Step 4 is the point at which the root locus branches leave or approach the real axis is called breakaway or break-in point. We have seen if you are having two poles, then we will be having the breakaway point. If you are having two zeros, then we will be having break-in point. And how we can determine breakaway and break-in point? By this formula, that is dk by ds is equal to 0. So this is fourth step. Fifth step is to determine at which angle our root locus branches is leaving or approaching the breakaway or break-in point, which is given by plus minus 180 by r. Mod r, where mod r is what? Mod r is the number of root locus branches leaving or approaching the breakaway or break-in point. Next step, that is step number 6. If the number of poles is greater than number of zeros, which is given by p minus z, then root locus branches terminating at infinite will be given by p minus z, right? So we have seen two conditions. When poles is greater than 0, then p minus z branches will terminate at infinite. If poles is equal to 0, that means no branches will terminate at infinite. Next step, that is step number 7. Number of root locus branches is equal to number of open loop poles equal to number of closed loop poles, or is also equal to order of the closed loop system, right? Step number 8, the root locus branches terminating at infinity will do so along a straight line which is given by asymptotes. So we have calculated asymptotes. You can see in here. So what is asymptote? Asymptote is given by alpha is equal to 180 degree 2q plus 1 p minus z, where q is, you have to pay attention here, where q value of q will be from 0, 1 to p minus z minus 1, right? You can, for different values of q, you can get different values of alpha as well. Now the point at which next step, that is point at which the asymptotes intersect the real axis is called centroid, which is you can calculate it by this point, that is summation of real parts of poles minus summation of real parts of zeros upon p minus z. The point of intersection of root locus branches on the imaginary axis can be obtained by Routh-Hurwitz table, right? Suppose if your root locus branch is cutting the imaginary axis, you can determine at what point your root locus branch is cutting the imaginary axis by building the Routh table. This is step number 11. Next step, that is step number 12. Angle of departure. We have seen why we calculate the angle of departure. That is for complex conjugate poles. We calculate the angle of departure, which is given by this. Next step, that is angle of arrival. We see for complex conjugate zeros, we calculate the angle of arrival, which is given by this. Then magnitude criteria. Magnitude criteria is given by mod of GH will be equal to 1. It is used to calculate the values of K and K at any point on the root locus. Next step, that is angle criteria. Angle criteria is the formula you can see is given by here. That is angle of G of H. Angle of will be equal to 2K plus 1 into 180 degree. Where K is equal to 0, 1, 2 to infinite. That means at any point on the real axis will be part of root locus is odd multiple. It is used to determine the shape of the root locus, right? So at this point, we have discussed 15 steps to draw the root locus, and if possible, we will be seeing all those steps in our solved examples. So one by one, we will proceed. We will start with the easier example, and then we will increase the concept complexities of that example, right? Okay. So what is the first question? You can see question number 1. Open loop transfer function has been provided to you, which is given by k upon s plus 1, right? So you have to follow all the steps. What is the first step? First step is to locate the poles and zeros. So what you can do, you can see this is real axis, this is imaginary axis. How you can calculate the poles? You can calculate the poles by equating the denominator equal to 0, so that means s plus 1 is equal to 0. So this gives s is equal to minus 1. So we are having poles at minus 1, and there are no zeros, right? Let us suppose this is minus 1 point. Now you can now here you can see there are how many number of poles are there. Number of poles is 1. How many zeros are there? The number of zeros are zeros. How many branches will terminate at infinite? Here p is greater than z. That is p minus 1 is equal to 1. So one branch will terminate at infinite. Now for this, you can calculate the asymptotes. That is angle alpha, and angle alpha, you can see it is given by this formula, 180 degree 2q plus 1, where q is equal to 0. Why q is equal to 0? Because q will range from 0, 1, 2 to p minus z minus 1, where p minus z is already 1, so p minus z minus 1 will be 0. So value of q will be is equal to 0 only. So you can substitute the value of q is equal to 0 here, and you will be getting angle of asymptote as minus 180 degree. Sorry, 180 degree. Now you have got the asymptote. You can calculate the centroid as well. So how you can calculate the centroid? I'm calculating here. Centroid is real part of poles. Poles is minus 1, and upon real part of zeros, so there are no zeros. Upon p minus z, that is 1. So centroid will be again minus 1. So what you can do? You can put your pen here, a point here, and then you can draw minus 180 degree here. So this is 180 degree line, right? And if you are here and you are observing to the right hand side, total number of poles and zeros are 0, which is even or which is not odd. So this will not be part of your root locus. When you are at minus infinite and you are observing to the right hand side, you can see that always there is one pole at the real axis, so which is odd. So that means this hole will be part of our root locus, right? Okay, so this is going from like this, right? And at open loop pole, we are saying that value of k is equal to 0, and 0 is lying at infinity, where gain k will be is equal to infinite. We are assuming that 0 is lying at infinity, and our root locus branches is also terminating at infinity at angle of 180 degree, right? So this is regarding this example 1. So you can see again, I'm telling you again. So number of poles here are 1, 0 is 0, no 0. So p minus z, there is one branch will terminate at infinite. That you can calculate by angle of asymptote. Then you can calculate centroid, and here you can see this is minus 1 point, and it is going like this, right? So this is regarding question example number 1. Now we will see next example. You can see g of hs is equal to gs into hs is given as k s plus 2 upon s plus 1, right? And so that means our poles, you can calculate poles is equal to, so poles is at minus 1, and zeros, s plus 2 is equal to 0, so zeros is at minus 2. So one pole is there at minus 1, one zero is there at minus 2. You can apply this rule number 1, and this will be part of our root locus branch, right? So one root locus branch will start at open loop pole, and it will terminate at open loop 0. Value of this will be equal to k is equal to 0, and here gain at open loop 0, the value of gain will be equal to infinite. So this is how the whole root locus branch or root locus will look like, right? Which you can observe in this case as well. So here number of poles is equal to 1. You can see number of zeros is equal to 1. No branches will terminate at infinite. It will start from at open loop pole and terminate at open loop zeros. You can see. So this is regarding the step example number 2. Let us just move to the next example. Slowly we will increase the complexity, right? So here you can see this is the next example. Total number of poles, you can see there are 2 poles, and total zeros there are 2 zeros. So p minus z will be equal to 0. You can see that means no branches will terminate at infinite. Now what you can do, you can locate poles and zeros. So you can see there is one pole at, so there is one pole at origin, another pole at minus 2, one 0 at minus 1, another 0 at minus 3. So let us suppose this 0, minus 1, minus 2, minus 3. And how your root locus branches will look like, you can, when you're observing here from here, you can observe to the right hand side. Total number of poles and zeros is 1, which is odd. So that means this will be part of your root locus branch. When you're studying here, observe to the right hand side. Total number of poles and zeros on the real axis is 3, which is odd. So this will be part of your root locus branch. If you are standing here and if you are observing to the right hand side, see that total number of poles and zeros will always be 2. So that means this will not be part of your root locus branch, right? And root locus branch will start from pole and terminate at 0. Start from pole and terminate at 0. At pole, the value of gain k is equal to 0. At 0, value of gain k is equal to infinite. So this is how this next example looks like. I've not drawn real axis and imaginary axis. I'm assuming that I'm leaving it up to you. You can see that this is our real axis and this is our imaginary axis and this is our S-plane. Okay, this is the example number 3. So you can see here again, number of poles is equal to 2, number of zeros is equal to 2. So P minus Z is equal to 0. No branches will terminate at infinite. One pole is at 0. Another, this is 0. This is pole. This is 0. Starting from here, terminating at here. Starting from here, terminating at here. Value of gain K is 0 here, infinite here, and infinite here. Right. Moving to the next example. That is GS HS is given by K upon S into S plus 1. Right. So let us just draw. There is one pole at origin and another pole is at -1. So you can see if you're, so this will be part of our root locus branch straight away. You now, I think you should be able to tell by yourself that this will be part of your root locus. And at this pole, value of gain K is equal to 0, gain K is equal to 0. And here from this, you can observe that P is equal to 2 and Z is equal to 0. So P minus Z will be equal to 2. So two branches will terminate at infinite. So you can see that we will be having our breakaway point here. How you can calculate the breakaway point, we have already seen by putting dk by ds is equal to 0. Right. So what we will be doing, we will be calculating dk by ds is equal to 0 by the characteristic equation. So that is 1 plus gs into hs is equal to 0 is our characteristic equation. That is 1 plus k upon s plus 1 will be equal to 0. And then you can take the LCM. Let me write this again. 1 plus GH is equal to 0. So 1 plus K upon S into S plus 1 will be equal to 0. Take the LCM. So this will be S plus 1 plus K will be equal to 0. So K will be equal to minus of S plus 1. K will be equal to minus of S square plus S. So dk by ds, you have to equate it to 0. So you can say minus of 2s plus 1 will be equal to 0. So s will be equal to minus 1 by 2. Minus 1 by 2 is our breakaway point, right? So you can see that again here number of poles is equal to 2, 0 is equal to 0. So P minus that is equal to 2. So that means two branches will terminate at infinite, which is given here. How that branches will terminate at infinite, you have to calculate the asymptote here. So Q in this case will be 0, 1, 2 to P minus Z minus 1. So P minus Z minus 1 will be equal to 1. So in this case, values, there will be two values of Q, that is Q is equal to 0 and Q is equal to 1. What you have to do, you have to put these values of Q one by one, and then you can calculate what is alpha. Alpha is equal to 2Q plus 1 into 180 degree upon P minus Z. So first you can put Q is equal to 0. If you are putting Q is equal to 0, so here you will be getting 180 by 2. That means you will be getting 90 degree. And alpha 2, when you put Q is equal to 1, you will be getting 3 into 180 degree upon 2. This will be equal to 270 degree. So you can see that I've already calculated here. So alpha is equal to 90 and 270 degree. Right? And breakaway point we have already calculated that is minus 1 by 2. That is here, right? Okay. So you can see that breakaway point I have already calculated, that is dk by ds was coming like this, and s breakaway point was finally minus 1 by 2. So you can see that one branch is starting from here, going like this. Another branch is starting from here. Value of gain k is equal to 0, 0. And asymptote we have calculated. What is the asymptote we have calculated? 90 and 270. And we need a centroid, right? Why we need a centroid? To draw. No, here we do not need a centroid. We are having this. We have already calculated here the breakaway point, right? And from breakaway point, you need to calculate at which angle it will leave the real axis. So that is calculated by here, plus minus 180 by r, right? And r is what? How many branches approaching that breakaway point? So there are two branches, right? One from -1, one from 0. So plus minus 180 by 2, that means plus minus 90 degree. One branch will go like this, another branch will go like this. And this is angle of asymptote. So if you want to, if I can draw it here, so just pay attention. So one pole is at here, another pole is at here. One branch is coming like this, another branch is coming like this. We are having a breakaway point. This is plus 90 degree. This is minus 90 degree. Angle of asymptote we have calculated at angle of asymptote we have calculated 90 and 270, and we have to also calculate centroid because we need to have some point to draw that angle of asymptote. Centroid is summation of real part of poles. The real part of pole is -1 minus summation of real part of 0, so there are no zeros. We will have minus 0 upon p minus z. P minus z is 2, so minus 1 by 2, that is equal to again minus 0.5. So that means this point is again our centroid. So you can draw an angle of 90 degree and 270 degree. I am drawing by dotted line. You can see this is my plus 90 degree and this is plus 270 degree. Now remaining root locus branch you can draw in parallel with this asymptotes. So this is how your final root locus branch will look like. Here the value of gain k, you can write k is equal to infinite, k is equal to infinite, right? So this is regarding the next example. Now we will move to the next example. Okay. So here the open loop transformation is given to you. You can see k upon k into s plus 1 upon s into s plus 2 plus s plus 3. So here you can see that number of poles here are 3, number of zeros here are 1. So p minus z will be equal to 2. So values, that means two branches will terminate at infinity. So accordingly you can calculate asymptotes, angle of asymptote, that is 90 and 270, right? And from here you can see that we are why we are calculating here, because we are having breakaway point, right? Breakaway point, you can see here we are having a breakaway point, and that breakaway point, how the root locus branches will leave from breakaway point is given by plus minus 180 by r. R is how many branches is approaching this point. So there are two branches is approaching this point, that is one from this pole, one from this pole, therefore plus minus 90 degree. Right. So let me just draw very roughly the poles and zeros of this for this question. Okay, there is one pole at -1, one zero at sorry, there is one pole at origin, one pole at -1. So this is -1, this is origin, one pole at -2, and another pole is -3. So from here to here, you can see that this will be part of our root locus, which is starting from here and terminating at this point. That is k is equal to 0, k is equal to infinite. There is no problem in this. So this is k is equal to 0, k is equal to 0. One root locus branches will start from here, and another will start from here, and they will intersect at some point. So here you have to calculate the breakaway point. How you can calculate the breakaway point? By putting 1 plus g h is equal to 0. So you can calculate the value of k, 1 plus k upon s plus 1, s plus 2, s into s plus 2, s plus 3. You can calculate the LCM here. You can take the LCM and you can equate it to 0. So k will be equal to minus of s plus 2, s plus 3 upon s plus 1. Then you can differentiate it with respect to s, and you can equate it to 0, and you can calculate the breakaway point. So you can see that 1 plus gs hs is equal to 0. You have calculated the value of gain k is here, and we have differentiated it with respect to s, right? After differentiating, you can calculate the values of s. You can see we are having minus 2.4, which is coming here. So this will be our breakaway point. So from you can see that this is a cubic equation. So that means you will be getting 3 roots. Now out of those 3 roots, you have to see which root is satisfying our present root locus condition. So let me again draw the root locus here. One pole at here, another 0 is here, one is here, one is here. Right. So this is -2. I think this is -3. This is -1. This is 0, and so here was our root locus branch where we need a breakaway point. So breakaway point, you can see minus 2.46, which is satisfying this criteria. Another 2 locations which you will be getting from this cubic equation will not satisfy this criteria which we are having. So minus 2.4, let us suppose approximately we are having minus 2.46 at this point. So at this point, our root locus branch will terminate, will leave the real axis, right? Okay. Now, what you have to calculate? You have to calculate the angle of asymptote as well, because how this root locus branches is terminating at infinite, you have to calculate that as well. So asymptote we have already calculated from in our previous slide. As you can see, we have calculated here 90 and 270 we have already calculated. Okay, and now we have to calculate the centroid, right? So centroid is, you can see, is calculated here. There is summation of real parts of pole minus summation of real parts of 0 upon p minus z. So you can see I have put all the values here, and centroid we are getting as -2. So -2, that means this is our centroid. So you can draw, this is plus 270 degree, this is plus 90 and plus 270 degree. So after breakaway point at plus 90 degree and minus 90 degree, this root locus branch will follow this asymptote, and it will terminate at infinite along this line. So you can say that this k is equal to infinite here, k is equal to infinite here, right? For clarity, let me draw this root locus branch again in the next slide. Okay, so let me redraw it. So this is our real axis, this is our imaginary axis. Okay, one pole is at here, another 0 is here, another pole is at here, another pole is at here, right? So we are having this 0, -1, -2, and -3. So we have calculated the breakaway point, and let us suppose this is our breakaway point, and this is centroid is like this. I'm drawing. Let me draw the centroid. -2 is our centroid, and this is plus 90 degree and plus 270 degree is our angle of asymptote, right? And so this much part is clear. Okay, so one root locus branch will start from here and it will terminate it here. There is no problem here. One root locus branch will start from this point, another root locus branches will start from this point. K is equal to 0 here, k is equal to 0 here, right? It will dissect and it will intersect and it will break away like this. One branch, root locus branch, will break away like this, another will break away like this at plus 90 and minus 90, and then after some point it has to follow the asymptote. That means it has to deviate a little bit and it has to follow the asymptote like this. And you know that it is symmetrical about the real axis. That means whatever is on the top right, top side, the same will be the on the bottom side. So this will go like this to infinite from here to here. So value of gain k is equal to infinite and infinite. Okay, so here we can see that number of poles were 3, number of zeros were 1. So p minus z, that means 2 branches is terminating at infinite. You can see one branch is here, one branch is terminating here. So this is the solution of this example. Now let us move to the next example. Okay, so now you can see this is a little bit more complex problem. So we will try to see what is given here, right? So directly from the open loop transfer function, you can see that poles is equal to 3 and zeros is equal to 0. So p minus z, that is total number of branches which will terminate at infinite, will be equal to 3. 3 branches is terminated at infinite, right? So that means you have to calculate alpha here and you have to also calculate sigma here. So alpha is asymptote and sigma is centroid. Right? So asymptote, and so here q will be equal to, so we will be having, since q p minus z is 3, so we will be having 0, 1, 2 to p minus z minus 1. So p minus z is 3, so p minus z minus 1 will be 2. So q values of, we will be having 3 values of q, 0, 1 and 2. You can put the values of alpha, you can calculate alpha 1, alpha 2 and alpha 3. 3 alphas, 3 angles will be there because 3 branches is terminating at infinite. And formula is 2q plus 1 upon 180 degree. Sorry. Formula is 2q plus 1 upon p minus z into 180 degree. So one by one you can put q is equal to 0, 1, 2. You will be getting the angle of asymptote. So you can see this is the angle of asymptote that I have already calculated, that is 60, 180 and 300 degree, right? And you can calculate the centroid. So real part of poles minus real part of zeros. So there are no zeros, which will be equal to 0. So you can see that centroid we have already calculated. Centroid is coming at -1. Okay. Now let's just so this point, up to this point, I think it is clear. So number of poles is equal to 3, 0 is equal to 0, 3 branches will terminate at infinite. You can see here alpha is equal to, this is angle of asymptote I've already told, and centroid we have already calculated, and this we will see shortly, right? So how this root locus branches is leaving the real axis. Okay, now let me draw the locate the poles and zeros and tell you from there. So there is one pole at origin, one pole at -1, one pole at -2, right? So from the previous step, you can easily tell that this will be part of our root locus branch, and from here onwards till infinite, this will be part of our root locus branch. Why? Because if you are standing at minus infinity, and if you're seeing to the right hand side, you can observe that total number of poles here are 3. So which is odd. So that means from minus infinite to this point, the whole real axis will be part of your root locus. Right, so this is one root locus branch which is starting from k is equal to 0 and terminating at k is equal to infinite. So one root locus branch is done. Now we have to worry about this. The value of k is equal to 0 here, k is equal to 0 here. Starting from here, so here we will be having breakaway point. So for breakaway point, what we have to do, we have to do dk by ds is equal to 0, right? So which you can see here, dk by ds is equal to 0, which I have calculated. So you can see that after this is the solution after the differentiation. So here we are getting two values of dk by ds. We are selecting minus 4.2 and we are rejecting minus 1.5. Why? Because this is not, this minus 1.5, minus 1.57 is not satisfying our criteria. Minus 1.5 will lie somewhere here, right? This is not our part of a root locus, so therefore we will not select. So therefore I have neglected this. Just pay attention here, and I have selected minus 4.24, minus 4.2. Minus 4.2 will lie somewhere here, right? And this will leave the real axis at an angle of plus minus 90 degrees. So this is plus 90 and minus 90. Now after this has to follow the asymptote, right? So asymptotes, so let me redraw it again. Let me redraw it again. So one pole is here, another pole is here, another pole is here, right? And so this is -1 and this is -3, -2. This root locus branch is starting from here and terminating at infinite. This we have already seen, right? And centroid is -1, and angle of asymptote we have got 60, 180 and 300. 60 means this is -1, this is 60 angle, this is -1, this is 180 angle, and 270 will be, sorry, 300 will be, this will be 300 angle. I have just drawn roughly, right? So do not worry. So this is angle 60, you can say. This is 180 and this whole is 300 degree, right? So one root locus branches which is starting from here, and one root locus branch is starting from here. After intersecting, they will leave the root locus and this will form like this. This will terminate at infinite through this asymptote only. K is equal to infinite, k is equal to infinite, right? Okay, now here you can see that this root locus branches is cutting the imaginary axis. That means you can calculate the value of s here from the route through its table. So what you have to do, you have to first calculate the characteristic equation, which I will be showing. So this is our characteristic equation. You can easily calculate. You can form the route table. After forming the route table, what you have to do, you have to make this row, or you have to make one row of 0. How you can make a row of 0? You can see one element is already 0 here. You can equate it to 0 and you can make it to 0. So that means 6 minus k will be equal to 3 is equal to 0. So 6k will be equal to 6. So gain 6, this root locus branch is cutting the imaginary axis. You can see from here as well. So this point, at this point, the value of gain k is 6. And if you want to calculate what will be the value of s, you can calculate through auxiliary equation. What is auxiliary equation? The auxiliary equation you can form just above the row of 0, right? So this is row of 0. You can calculate the auxiliary equation, that is 3s square plus k is equal to 0. You can substitute the value of gain k. So gain k is 6. Then you can calculate the value of s. So here s is equal to plus j root 2. Here minus j root 2. Right. So here you can see the whole root locus is drawn here. So let me explain in this on itself. So this is 1 0 at here, another 0 is here, another 0 is here. One branch is starting from here, k is equal to 0, terminating at infinite here, terminating at infinite here, terminating at infinite here. So 3 root locus branches has terminated at infinite. So this is our breakaway point. You can see one branch is leaving like this, another branch is leaving like this, and then it is following the asymptotes, right? And value of gain k here at this point is 6. So you can see 6, and value of s is plus j root 2 minus j root 2. So this is the whole root locus will look like. So from k is equal to 0 to 6, our system will be stable. Why it will be stable? Because the poles are on the left hand side. You can see the poles are on the left hand side only. At gain k is equal to 6, our poles are on the imaginary axis, then that means our system has become marginally stable. And when gain k is greater than 6, our system will be unstable. So this I hope you all of you know that if any poles is lying on the right hand side, then your system will become unstable, right? So let me explain this in the graph as well. So from this point onwards to this point, our system will be stable. When your roots are on this point, our system will be marginally stable. When your roots will be here, your system will be unstable, right? Okay, so this is our next. So let us just move to the next problem. Okay, so you can say that we are having the next problem. Open up transformation has been provided. K upon s square plus 2s plus 2 into s plus 2. Find the angle of departure from -1 plus j. So you can see we are having complex conjugate poles, which is given here. So if I draw the s plane, so we are having one pole at -2, one pole at here, another pole is at here. So this point is given by, this is -1 and this is plus j. This is -1 and this is minus j. So what it has been asked, you have to calculate the angle of departure for this pole. Why angle of departure? Because root locus branch will start from here. That is k is equal to 0 will be here. Gain k will be, value of gain k will be 0 here, right? And three branch, it will have 3 root locus branches, and all the 3 root locus branches will terminate at infinite. Okay. So now how can we calculate the angle of departure? So, and if you know that angle of departure is given by 180 degree minus phi p minus phi z, right? Where phi z is the angle contributed, net angle contributed by all other zeros, and phi p is net angle contributed by all other poles to the pole under consideration. So that means this pole is under consideration. So how you can calculate phi p? One phi p will be from here, another phi p will be from here. So this you can directly see that this is 90 degree, and this is 1, and this is also 1. So I think this will be 45 degree. So phi p will be equal to 45 degree plus 90 degree, right? You can see that this is 135 degree. So phi d will be equal to 180 degree minus 135 degree. That will come out to be 45 degree. So phi d for here will be 45 degree. 45 degree, that means if this is our axis of reference, 45 degree from here will be here, right? So the root locus branch will start at this angle, I guess. So you can see the same thing I've shown here. So this is one pole, another pole. You have to calculate the phi d for this point, -1 plus j. So the angle, the formula is 180 degree, phi p plus phi p minus phi z. Phi p is 90 plus 45, that is 135 degree. The phi d1 will be is equal to 145 degree. You can see, sorry, only 45 degree. And phi d2 will be similarly, it will be the mirror image. Okay, so you can see phi d1 is 45 degree and phi d2 is minus 45 degree. Okay, so 45 degree, that means it will be here, right? So what has been asked in the problem, you have to calculate the angle of departure for this pole, and for this pole the angle of departure is plus 45 degree, right? So this is the solution for this problem. Let us just move to the next problem. Okay, so here the total root locus of that problem has been explained. So let us just see through that again. So as you can see, that there are two poles and there is one pole here, right? So you have to draw the root locus for this pole. So here you can see p minus z is equal to 3. So 3 root locus branches will terminate at infinite. So that means you will be needing alpha. So alpha is equal to, you can see alpha we have calculated from here, that is 60, 180 and 300. And you have to also calculate centroid. Centroid you can calculate from this formula, that is real part of pole minus real part of zeros. So centroid is coming out to minus 1.33. 1.33, suppose this is -2, this is -1. So minus 1.33 will be somewhere here. So from here you have to draw the asymptotes. So this is 60 degree, this is 300 degree, and this is this is 60 degree, and this is 180 degree, and this is 300 degree, right? And we have also calculated the angle of departure. Angle of departure we have calculated, that is 45 degree. So that means if suppose this is the 45 degree, the one root locus branch will start from here, and through this it will terminate at infinite. And so at bottom side it will be just mirror image. It will start from here and it will terminate at infinite like this. Just by rough hand I have drawn. So again here you can see, and this is value of gain k is equal to 0 here, value of gain k is equal to 0 here, gain k is equal to 0 here. From here the root locus branch will start from here and it will terminate at infinity for this root locus branch. Other two root locus branch which is terminating at infinite is given by here and here. So you can see again it is crossing the imaginary axis, so you can calculate the value of gain k at this point and value of s at this point by Raoult-Hurwitz, so which is given here. So you can see that I have calculated the characteristic equation here, and once having the characteristic equation you can form the Raoult table and you can equate this to 0 to calculate the value of gain k. So when we are equating it to 0, you can see that k is equal to 20 degree. Gain k is equal to 20. That means at this point the value of gain k is 20. At this point the value of gain k is 20. So how you can calculate the value of s? You can calculate the auxiliary equation from here and you can substitute the value of s. So s will be plus minus j root 6. So here the value will be plus j root 6 and here minus j root 6. I hope this is making sense, and this is the final root locus branch you can see. So I will be explaining you this point. So you can see that there are two poles here and here, and there is another pole which is here. So value of gain k you can see here at 0, starting from here and terminating at infinite here, right? So this is one root locus branch. Story over. Next is we have to calculate the centroid as well. So centroid is minus 1.33. So this is angle 60, this is angle 180, and this is minus 300. Why we have drawn centroid? To draw the angle of asymptote. Why we have drawn angle of asymptote? To see how our root locus branches is terminating at infinite, right? Now since we are having the complex conjugate poles, we have to calculate the angle of departure. So you can calculate the angle of departure for this, and for this bottom pole it will be just the mirror image. And once we have calculated the angle of departure, we have calculated it to be 45 degrees. So you can see that this angle is coming out to be 45 degree. So for similarly this angle for bottom it will come out to be minus 45 degree, right? And you can see that it will start from here and it will terminate at infinite. It will start from here and it will terminate at infinite along the asymptotes. And you can see that this branch is cutting the imaginary axis at these 2 points. So you can calculate the value of gain k and s from the Raoult-Hurwitz table, right? By making it the concept of rows of zeros. So which we have seen here. Okay, so which we have seen here. You can see we have calculated the characteristic equation and we have formed the row of 0. Why this will be a row of 0? Because if we make row of 0, you cannot make row of 0 here because there is a constant here 4, right? So therefore you have to make rows of 0, this rows to be 0, and this row will only be 0 when this term will be equal to 0. So that is why we have equated it to 0 here. You can see, and value of gain k we are getting. Once you got the value of k, it is very easy to calculate the point. How you can calculate? You can calculate by the auxiliary equation. So this is the power is s square, so this will be 4s square, 4s square plus 4 plus k you have already calculated. So you can see 4s square plus 4 plus k. Value of k we have already calculated, that is 20. You can substitute the values and you can calculate the values of s. So values of s is coming out to be plus minus j root 6. So this is only what has been shown here. You can see the value of s is equal to plus j root 6 and value of gain k is 20. So this is the end of our discussion. I hope you enjoyed it, and I will be uploading the questions related to the GATE exam. So you can study those questions and I will be also providing the solution. And if you're having any doubt, you can contact me at my email address. Thank you so much for listening.